So in this video, we're going to come back to the question that we asked before, which is how many roots can a polynomial have? And there's a specific result that we can already derive based on what we know. It's not the final answer, but it already hints a bit at what the answer will be. So it says that a polynomial p of x, and here we exclude the trivial case where the polynomial is all zero, cannot have more than n distinct zeros where n is equal to the degree of the polynomial. So recall, if our polynomial is written as a times x to the power n plus b to the power x minus n plus dot 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 other terms, then the degree is the highest exponent that you have, so it's this n. Degree, the highest exponent. And so we can derive this from the remainder theorem. Assume that there are m roots with m strictly bigger than n, and call these roots alpha 1, alpha 2, dot dot dot, alpha m, just as we did for the remainder theorem. Then, according to the remainder theorem, we know that p of x has a factor x minus alpha 1, x minus alpha 2, all of the factors multiplied together, x minus alpha m, times some quotient q of x. And now you can see a bit what happens here. So if you multiply all of these linear factors together, you have m of them. So this is a degree m polynomial. If you multiply this out. This q thing that you have here, we don't know what it is, but it's a polynomial, and we know its degree is going to be 0 or 1, but its degree is going to be bigger than or equal to 0. And what do we have on the left-hand side? Well, we have our polynomial p, and that is of degree n. So we have something on the left-hand side that's degree n, and here on the right-hand side we have something that's degree equal to m or strictly larger than m, so at least m. And that gives us a contradiction, because we have two polynomials on the left-hand side and the right-hand side. If they're equal, their degrees also have to be equal, but here we have a degree n, and here we have degree at least m, and we know m is strictly larger than n. So that means that our assumption here was false, and therefore we conclude that it is impossible that there are m roots with m bigger than 1, and so the number of distinct roots has to be less than or equal to n. This is, by the way, this is an example of a proof by contraposition, where you make an assumption and then you reason until you find something that is impossible, and then you can decide that your assumption was false. So here our assumption was that there are more roots than the degree of the polynomial. We found that a contradiction, so therefore we conclude that the opposite holds, that there are fewer roots than the degree. So for this next section, we're going to look at what are called symmetric polynomials, which are specific combinations of roots of a polynomial. And what this is allowing us to do, what this is going to let us do, is establish a relation between the roots and the coefficients of a polynomial. And in order to see how this works out in practice, let's look at an example first. So here we're going to multiply out the following factors: x minus 2, x minus 3, x minus 7. And we're going to do this in a very slow and careful way. So for the first two factors, I'm not going to do all the algebraic simplifications. I'm just going to write it as x squared minus 2x minus 3x plus 2 times 3, and then times x minus 7. And now I'm going to multiply the third factor with that, and I get x cubed minus 2x squared minus 3x squared plus 2 times 3x, and now minus 7x squared plus 2 times 7x plus 3 times 7x minus 2 times 3 times 7. So I have these roots here, and I didn't do any algebraic simplification. So it's painful, but it's going to show us an important thing to keep in mind. So now let's collect all the terms in x cubed and in x squared. So in x squared we have 2 plus 3 plus 7 x squared. And now in x we get 2 times 7 plus 3 times 7 plus 2 times 3 x, and then the constant term is minus 2 times 3 times 7. And now let's look at what we obtained here. So what we see is that for the coefficient of the x squared term, we have the sum of the roots, or the negative of the sum, if you want to be precise. For the coefficient of x, we get sums of pairs of roots multiplied together, and then for the constant term we get all the roots multiplied together. Or again, the negative of this. And this is also true in general. So now we can extrapolate to the general case, and I'm just going to state this, but it's almost always easier to calculate with an example than to use the general formula here. So if we define the symmetric polynomials as follows. call these symmetric polynomials, even though they're not actually polynomials. We let S1 be the sum of n complex values. We let S2 be the sum of pairs, so A1, A2 plus A1, A3 plus and so on A1, AN, and then plus A2, A3, and so on, plus A3, A4, plus dot dot dot. So you take any two values A and you multiply them together and you sum all of this together. That gives you S2. And then S3 is doing the same thing but with three values, A1, A2, A3, plus A1, A2, A4, plus dot dot dot. There's going to be a wide variety of terms here. And you keep doing that until you get Sn, which is all the values A1, A2 up until An multiplied together. So if we have these auxiliary quantities, then we have the following nice result. Then x minus A1, x minus A2, dot dot dot, x minus An is a polynomial, and we can write it down exactly what it is. It is going to be x to the power n minus S1 x to the power n minus 1 plus S2 x to the power n minus 2. And then you keep doing this, so you alternate the signs and you increase the degree of s and you decrease the degree of the polynomial, dot dot dot, until you get at the end plus minus 1 to the power Sn. So that's our constant term. I do not recommend that you memorize this particular expression. If you have to do something with the roots, and there's a couple of examples in the exercises, then I recommend that you focus on a specific case and then do what I did here and try to rederive the formula from scratch. So in order to see how this works on an example, let's look at the following problem. So given a polynomial p of x, where p is x cubed plus 2 times x squared minus 3 times x minus 1, find the expression for alpha squared, or find the value of alpha squared plus beta squared plus gamma squared if these unknown quantities alpha, beta, and gamma are the roots of p of x. So you might be tempted to say, to solve this, I need to find the roots. Don't do that. It's going to be a lot of work, and sometimes it's going to be impossible to find the roots. Use some trickery with symmetric polynomials to find the answer without calculating the roots. So in particular, what do we know? Well, in general, if we have a polynomial p of x given by a times x to the power 3 plus b times x squared plus cx plus d, then we know there's going to be up to 3 roots of this, and we can relate the roots with the coefficients a, b, and c, because we know the first coefficient here is going to be more or less the sum of the roots. This one is going to be the sum of pairs of roots. And the last one here is going to be the product of the roots. And so now if we write that mathematically, then the first expression here, we have that the sum of the roots is alpha plus beta plus gamma. and we can relate that to b, but here we have to be careful for two things. We have to divide b by the coefficient of the leading term, and we have to put a minus here. Why those two things? If you go back to the expression that we had on the previous slide, then you also see the signs alternate, so it's minus, plus, and so on up until the last term. And also keep in mind here what we have a monic polynomial. There's no coefficient here in front of x to the power n. So if you want to say something, as in this case about a polynomial that has a coefficient for the x cubed, then we have to divide our coefficient by a. So the sum of the roots equal to minus b divided by a. Now, for the second term, we know sums of pairs. What is that? Well, alpha, beta, plus beta, gamma, plus alpha, gamma. That's all the sums of pairs. And that's equal to, so again, we have to alternate the signs. So it's plus, we take the coefficient c, and we divide by a. And then the last one, so d, here that's going to be equal to the product of all the roots, alpha, beta, gamma, and that is minus d divided by a. So again, make sure you alternate the signs, minus, plus, minus, and divide by a, the coefficient of the leading term. So that gives us three relations that we know about our roots, and now we can fill in values. We get alpha plus beta plus gamma is minus 2 for our polynomial. Alpha beta plus beta gamma plus alpha gamma is minus 3. That's c divided by a, and alpha beta gamma is equal to plus 1. And so now, to come back to our problem, we want to know the value of alpha squared plus beta squared plus gamma squared. That's slightly different from what we know from the fundamental relations, but we can derive that by saying, well, this expression is equal to alpha plus beta plus gamma squared minus 2 times all of the double products, alpha beta plus alpha gamma plus beta gamma. And this is good because now I know that alpha plus beta plus gamma, that's minus 2. The sums of the double products, that's minus 3. So I'm left with minus 2 squared minus minus 3. So that's 4 plus minus 2 times minus 3. So 4 plus 6, or 10 for alpha squared plus beta squared plus gamma squared.